When NASA was looking to get back to the moon, it did look at resurrecting the Saturn V rocket. After all, it had delivered men to the moon from 1969 to 1972 with no failures of the rocket itself. But to do that, NASA and the contractors who built it would have had to go back to decades-old technology and working methods using highly skilled engineers, all of whom are either retired or no longer here. I did a video 5 years ago looking at why we could not remake the F1 engine today, but in those 5 years additive manufacturing has come on in leaps and bounds and now represents an alternative future not only for rocket engine design and manufacturing, but also for the whole rocket assembly itself. So let's see if NASA could remake a new modern F1 engine today. As we are dealing with engineering initiative, this would be a great time to show you one of the coolest things I've seen in a while, the hover pen from Novium. And no, this isn't a video trick. The hover pen really does hover, balancing gravity with a magnetic field to tilt at a 23.5-degree angle, the same amount as the Earth on its axis. Novium creates unique, innovative, high-end products that inspire curiosity and develop creativity. This high-end writing pen is made from aircraft-grade aluminium and oozes technical sophistication, comes from a company co-founded by a physicist, and is as much a piece of installation art as it is a writing tool. The super smooth and accurate rollerball makes writing a breeze. The powerful proprietary neodymium permanent magnets need no power and only lose about 5% of their magnetism every 100 years, so your hover pen will continue to hover hundreds of years to come. This Interstellar edition received the award for one of the best inventions of 2022 by Time magazine. Available in Space Black, Starlight Silver, Mars Magma and Neptune Blue, the hover pen makes an original and timeless gift idea, not only for loved ones, but with Christmas coming up, you could also treat yourself too. There are also premium editions in 18-karat gold, as well as one with a shard of real meteorite embedded in the body. The Future edition combines a 2-in-1 fountain and rollerball pen with interchangeable tip and a premium version which also comes with an 18-karat gold nib. Order your hover pen today and get not only free shipping but a 10% discount using the code CuriousDroid at the links in the description below, and you too could have this unique piece to adorn your desk at work or at home. The Rocketdyne F-1 engine was a miracle of engineering, which made it not only the most powerful single-chamber rocket engine ever built, but also one of the most reliable, with no major failures on all of its flights to the moon and later to place Skylab, the first US space station, into orbit. Each F-1 was more powerful than the combined output of 3 Space Shuttle main engines, but making the F-1 was a major undertaking, with each one hand-built and no two exactly the same, as improvements from mission to mission took place. Back in the day, manufacturing techniques included machining thousands of parts which made up the engine, and then assembly by bolting, welding and brazing. In fact, that's how most engines are still built today. To give one example would be the regenerative cooling of the thrust chamber. The most obvious thing about the F-1 engine was the large bell-shaped nozzle which accelerates the hot gas to produce thrust. There are 2 parts to the nozzle, the upper part or thrust chamber and the lower nozzle extension. The problem was that the gases in the upper part were burning at up to 3,200 degrees Celsius, easily enough to melt the metal of the nozzle. The solution was to cool the upper thrust chamber with some of the RP1 kerosene fuel before it was mixed and burned with the liquid oxygen. This was done by making the thrust chamber out of 178 primary down tubes, and then split each one into parallel tubes and then 178 alternate up tubes. These were braced together in the shape of the nozzle and then held in place by a series of lateral bands which gave the nozzle its strength. The tubes themselves were heavily jacketed to give some direct protection from the hot gas inside the thrust chamber. Approximately 70% of the RP1 fuel was diverted into the down tubes before returning in the up tubes into the manifold to be sent onto the injector plate to be burned. A separate gas generator drove a turbine at 5,500 RPM, producing 55,000 horsepower or 41 megawatts, which drove both the fuel and liquid oxygen pumps. The fuel pump delivered 976 litres of RP1 per second, of which about 680 litres of fuel per second were pumped through the tubing which made up the thrust chamber walls, and this was enough to keep the metal from melting. The material the tubes were made from was Inconel X750, a high-temperature, heat-treatable nickel base alloy. But because it was made from nickel, it wasn't very ductile and it was very difficult to work. Now this is where the huge amount of skill and metalworking knowledge had to come in. With all these separate tubes, joins and supporting bands, each F1 had over 900 metres or 3,000 feet of joins between the tubes that had to be braced together, and everyone had to be inspected to make sure there were no leaks or bad connections. This very complex build operation was repeated for each engine, making them both slow to produce and very expensive, and this is just one part of the F1 engine. The way they were built is a product of the times and the technology available. Since then, there have been major changes not only in engine design but also build techniques and the materials used, all of which require different skills to that used on the F1. One particular technology wasn't even thought of in the late 1960s was 3D printing. Yes, the same thing that we can now do in our homes with a few $100 3D printer to make almost any small-shaped object out of tiny layers of extruded molten plastic. 3D printing takes a virtual computer-generated object, then digitally slices it into very thin layers, which are then printed layer by layer on top of each other to build up the complete computer-generated object, but in real life. This is almost the polar opposite of conventional manufacturing, where you start off with a block of raw material, like steel for example, then process it in various ways to shape it, drill it and mill it into a new component, building up complex machines and shapes from smaller, simple ones. Even casting into a mould still requires machine work to produce the finished item, and this is only suitable for certain applications. It was in 1981 when Dr. Hideo Kodama invented one of the first rapid prototyping machines that created parts layer by layer using a resin that could be polymerized by UV light. In 1988, Carl Deckard, a student of the University of Texas, licensed selective laser sintering or SLS technology, another type of 3D printing that uses a laser to sinter powdered materials like metals into solid structures. Since then, there have been many advances in this technology which offers ways to make components out of metal that would be impossible to do with traditional machine work. One such of these would be the thrust chamber of a rocket. Instead of all the tubes and bands and associated metalwork we saw in the F1, a far better thrust chamber could be made in one piece, built up layer by layer with all the cooling channels fabricated within the nozzle walls and with the optimum flow requirements built in. This can be made in a fraction of the time and with much less material than it would with traditional methods. Almost anything can be made in this way using a variety of metals like 316 stainless steel, Inconel, titanium and other alloys. And now dual metal prints can be done in one process. In 2015, NASA successfully tested a 3D printed version of the gas generator that powered the fuel and LOX pumps used in the F1 engine and continues to compare the strengths and weaknesses of additive manufacturing to that of traditional forging and welding. One company that has taken the lead in 3D metal printing is Relativy Space. This was co-founded by Blue Origin engineer Tim Ellis, who started the Blue Origin's 3D metal printing division. Relativy Space's goal is not only to 3D metal print rocket engines, but the entire rocket body itself. Even though the company is only 7 years old, it's already launched the world's first 3D printed rocket into space, the Terran 1. The company has also worked with NASA to help produce the copper alloy GR-COP42 or Glen Research Copper 42 for use in combustion chambers of high-performance rocket engines. The GR-COP family of alloys was developed by Dr. David Ellis when he was a NASA-supported graduate student during the Space Shuttle era. At the time, the Space Shuttle main engine combustion chamber liners were typically replaced after 1 to 5 missions, but with the use of the then GR-COP 84, this could be easily increased to 100 missions between maintenance services and 500 missions for the engine life. GR-COP is a combination of copper, chromium and niobium and is optimized for high strength, high thermal conductivity and high creep resistance and will tolerate temperatures up to 40% higher than traditional copper alloys. GR-COP was used to 3D print the Eon 1 engines which powered the Terran 1. GR-COP pairs well with laser powder direct energy deposition, a method of additive manufacturing. Here, a laser creates a melt pool and the powdered GR-COP is blown into the melt pool, creating a solid material. A robot produces the 3D motion to direct the building process to create the entire part with the laser and blown powder. This is one of a variety of manufacturing methods used today, and it allows for much larger parts to be produced, but with fewer finer details. Relativity Space has also created the world's largest 3D metal printer called the Stargate, which is used to make the main rocket body. Using existing wire welding technology, it builds up the structure, including the fuel tanks, out of aluminium and virtually eliminates welding and fixings and only requires a minimal amount of machining for the joint flanges. This advanced technique even makes the shape slightly wrong to allow for the pressure of the fuel inside it to correct it at launch. This allows the thickness of the walls of a rocket to be thinner in comparison to that of a Coke can, and makes the whole rocket lighter and stronger, which either can use less fuel or carry a bigger payload. Relativity Space say that they can make a complete rocket from raw materials in just 60 days, allowing the same fast-fail prototyping method as used by SpaceX to greatly speed up development, namely make it, break it, and then remake it better. The main aim of the Terran 1 launch was to prove the viability of additive manufactured structural parts in a real launch, which made up 90% of a vehicle by mass. The Terran 1 was 35 meters tall by 2.3 meters wide and used 9 Eon 1 rocket engines and was launched on the 23rd of March 2023. Although it passed max Q successfully, that's the point where the maximum stress on the rocket structure occurs, the second stage failed to ignite due to a slower than expected opening valve and vapor getting into the LOX turbo pump, causing the mission to fail before it could get into orbit. Relativity Space has subsequently dropped the development of the Terran 1 in favour of the Terran R, a much larger and partially reusable rocket, and the much larger Eon 1 R engine, again both 3D printed. Ellis has said that this is to be a Falcon 9 sized 3D printed rocket with aims to launch an even larger payload due to the efficiencies gained by the additive manufacturing process. So what about Aerojet Rocketdyne making a modern day 3D printed F-1 with all the advantages that have been learned over the past 50 plus years? Well, if you'd have asked that question maybe 10 years ago, then the answer would probably have been no. But with the rapid progress of additive manufacturing and companies like Relativity Space and materials like GR-COP24, it now seems far easier to accomplish. Whether such a large rocket engine would be used compared to the Starship method of lots of smaller engines is another matter, and although it would be nothing like the original F-1, its 3D printed spiritual successor, should it be built, could go on to do for future space missions what the F-1 did for the moon missions. So I hope you enjoyed the video, and if you did, then don't forget to thumbs up, share and subscribe, and remember your 10% discount and free shipping if you order your hover pen today.